One way to think about the geometric distribution is as the number of trials, the distribution of the number of trials until the first success. And so we saw two alternative parameterizations of that. One was the number of tosses, and one was the number of tails, number of failures before the first success. What we're going to talk about now, the negative binomial distribution can be thought of as a generalization of the geometric distribution, as we'll see. So the negative binomial distribution. What is the negative binomial distribution? It has two parameters, P and R. Okay. And P is a number between 0 and 1. It's a probability, just like in the geometric and the Bernoulli cases. And R is an integer, 1, 2, etc. And it is the distribution of the waiting time WR, which we define as the waiting time, the number of tosses until the rth head in successive independent tosses of a P coin. So in our first definition of the geometric distribution, what we did was we thought about the waiting time W as the number of tosses until the first head. So this would be R equals 1. And in this case, we can generalize that to the number of tosses before the rth head, right? So if R is equal to 3, then this sequence here is going to give us a waiting time of 8. So how do we calculate the probability mass function? Well, the minimum value that this random variable can assume is R, right? If we're going to toss at least, we have to see R heads, we have to toss the coin at least R times to see R heads. And in general, the mass function, the probability that the random variable, the waiting time till the rth head is K. One way to think about that, well, how do we get R heads? How do we get the rth head to occur exactly on the kth toss? Okay, well, what do we need to happen is we need exactly K minus 1. No, I'm sorry. Exactly R minus 1 heads in the first K minus 1 tosses, and a head on the kth toss. So that's how we would break this event down, is that we have R minus 1 heads in any order at any point in the first K minus 1, but then we need the kth toss to be a head. Okay, so the first piece of this is like a binomial, right? Is that, well, if we have R minus 1 heads in the first K minus 1 tosses, then we have, how are we going to think about this? Well, it's K minus 1, choose R minus 1. P to the r minus 1. This is just the binomial distribution. 1 minus p to the k minus r. That's the binomial piece. And then we have one more trial that has to be ahead, so it happens with exactly probability p. So a way to write this is k minus 1, choose r minus 1. P to the r, 1 minus p to the k minus r. This is for values of k from r, r plus 1, etc. Another way to think about this, though, is not as the number of tosses until the first head, but as the number of tails before the first head, the number of failures before the rth success. So number of failures, well, that would be tails, before the rth success. And the rth success is a head. So in the example up above, here, oh, okay. So right here, if r is 3, we're going to write this as v sub r. V sub 3 is equal to 1, 2, 3, 4, 5, which is equal to w sub r minus r, right? 8 minus 3. So v sub r is going to be wr minus r, right? Number of tails before the first head. And we can derive the mass function of v sub r directly from the mass function for w sub r, right? So v sub r is equal to k only if w sub r is equal to k plus r. Okay. And the probability that w sub r is equal to k plus r, we already know. Well, it's k plus r minus 1. Choose r minus 1. P to the r, 1 minus p to the k. And this is for values of k equal to now 0, 1, so any non-negative integer. Okay. So these are two different ways to look at it. Where does the negative binomial, so these are two different ways to describe the same distribution. And you might have a preference for one over the other in a given context. You really only have to remember one. And you should probably just remember the one that you understand the best or that's easiest to remember. And that'll be different for different people. Where does negative binomial come from in the name? Well, one way to think about it is like this. We have this binomial component in the mass function. So this is in this mass function, okay? I can rewrite this, of course. R plus k is equal to k plus r, no problem there. The definition of this is r plus k minus 1 fall r minus 1 divided by r minus 1 factorial. Oh, I'm sorry. I can rewrite the top as r plus k minus 1. I can rewrite the bottom actually as k, right? Why? Because in general, n choose I is equal to n choose n minus I. So that's just an identity, which if you're not fully comfortable with that, let's make sure to do that as an exercise to verify. And so we use that here. And when we use that here, what we get is on the top. So what this is equal to is r plus k minus 1, r plus k minus 2, etc., all the way down to r plus 1 to r, and the denominator is k factorial. Okay, so now something that we can do interesting about this is that there's actually, so you can see that there's k terms up here. And let's take a -1. Let's think about taking a -1 out of each of these terms. So we take a -1 out of r, we're going to end up with -r. So first of all, there's k terms, right? So I'm going to multiply by -1 to the k, and I'm going to multiply by -1 to the k again. So -1 times -1 is 1. So multiplying by 1 is a common trick in probability. Figure out how to add 0 or multiply by 1 and rewrite certain expressions, and it simplifies the expression. And here we're multiplying by a clever version of 1, which is -1 times -1, k times. So this minus in front of the r is going to cancel with one of the -1s in this -1 to the power k. But we're going to do this for every single term. And if we do this, what happens? Well, what happens is we get a different expression. The expression is that this is equal to -1 to the k minus r choose k. So we can write minus r choose k because remember the definition of n fact of n choose I is n fall I over I factorial. So it's not, so this is the definition we're working with. There's a finite number of terms here, I, and so to put a negative value there is fine because we just do -1, -1, -1 minus 1, -1 minus 2, etc., up until the I term, -1 minus I plus 1. And if we write it this way, we end up with probability BR equals K, can be expressed as -1 to the K. Oh no, well, yes, -1 to the K minus R choose K, P to the R, Q to the K. And of course, Q is equal to 1 minus P. And the nice thing is that the -1 here can be folded into this Q, and what we're left with is minus R to the K, P to the R, minus Q to the power K, for all values of K from 0 to infinity. Okay. All right, so that's the mass function. There's three different ways to write it, and that's where the negative binomial name comes from. It's just good to know the different parameterizations and different ways to read this because different books will parameterize it differently, and they might not say exactly what they're doing or how to interpret it. So it's important to understand and to know where it comes from. Okay. We want to calculate the expectation and variance of the negative binomial. How can we do that? Well, we could try a bit of a brute force approach where we try to work through the weighted average of the mass function as we normally do, maybe find some kind of trick like we have, and then go from there. However, there's actually a quicker way and an easier way to do it. The quickest way to do it is to understand that the expectation, so in terms of waiting time, so WR for the example that we gave above. The example we gave above is here. And one way to think about this is, well, in order to wait for the third head, in this case, first we have to wait for the first head. Then we start over again. We wait for the next head. And then we start over again and we wait for the next head. And everything's independent of everything else, remember. So remember in this coin tossing, if it doesn't matter what's happened in the past, everything's independent for the future and looks the same. So one way to think about this is to say, well, this is actually x1 plus x2 plus x3, where x1, x2, x3 are independent geometric p random variables, right? This is the waiting time until the first head. X1 is the waiting time until the first head. X2 is also distributed as the waiting time till the first head. It just happens to be the second head in the sequence when we look at it as a whole. So in general, we can write WR as the sum x1 plus x2 up to x sub r of independent are independent. So that's sometimes how I write it, but I'll write it as independent geometric P. And if we do that, well, what can we say then? Well, we know the expectation of the geometric and we know the variance. So the expectation of WR in this case, it's the expectation of this sum, x1 up through xr. Expectation of sum is sum of expectations, and we know the expectations are 1 over p. So this is r over p. It's 1 over p, r times. For the variance, well, that's the variance of the sum. The variance of the sum of the variances plus twice times the sum of the covariances. Well, the covariances are 0 because we've assumed independence. That's 0. And now we just have a sum of the variances. So let's check back with what we already calculated. In the case of the geometric distribution, we calculated the variance of W, the waiting time, right, is 1 minus P over P squared. This is going to be R times 1 minus P over P squared. Okay. Now, that's a nice trick, and that's a quick way to do it. We do want to be able, if we can, and if we have to, calculate it the old-fashioned way. So that's approach number 1. Approach number 2 would be, we know that the expectation of a random variable is the sum over all possible values of k times the weighted average, probability weighted average of the possibilities. So in this case, we know that k goes from r to infinity. And then the mass function for WR we've already written down up here. K minus 1 factorial, K minus 1 choose R minus 1, P to the R, K minus to the, so K minus 1 choose R minus 1, P to the R, Q to the K minus R. Okay. So now when we see a sum like this, when we see an expression like this, really there's a few ways that we can proceed. We've seen in the geometric case that maybe we can express this as a derivative of some kind. That's one way. Another way is to somehow rewrite it as the probability mass function, as something out in front, so some constant times a sum, where the thing we're adding up, the thing we're summing over, is it can be identified as the mass function of some other distribution. And any distribution, it doesn't matter what the distribution is. The bottom line is, if we can do that and it's over all possible values of that distribution, then what happens is we know that the sum over all possibilities, sum over all the possible probabilities in a given distribution has to add up to 1. Probabilities always add up to 1. So in this case, with K minus 1 choose R minus 1, and we have a K out in front here. So we have K equals R to infinity. K minus 1 on the top is K minus 1 factorial times K, which is just K factorial, right? K times K minus 1 factorial is K factorial. We're left with R minus 1 factorial and then K minus R factorial. And still P to the R, Q to the N minus R. So now what we have is we have something that's kind of like K choose R right here, but not quite, because there's a missing piece in the denominator. So we need to add an R on top and an R on the bottom. And if we do that, we're gonna have K choose R. One of the R's on the bottom gives us a K choose R, and the R on the top is a constant, so it comes out of the sum. And we want this to now start to look like the negative binomial of a different distribution with different parameters. And since we have K, K is fine, but we have R here, and so it should be R minus 1. So it's the number of heads that we need to see minus 1. In this case, it's saying it's got to be R plus 1 head. So we can multiply by P on the top, P on the bottom to get P to the R plus 1. So one of in the numerator, it comes to the P to the R plus 1, and the denominator can come out here as a constant. This should be 10. And we have Q to the K minus R. But what is this? What does this tell us? Well, this is exactly the probability mass function of the negative binomial. So we say that, I'm sorry, I didn't say this up here, but WR has the negative binomial distribution with success probability P and number of successes R. So this is written as negative binomial P R. Okay. NB P R. So this is actually the NB P R plus 1. Okay. And so what we're left with is this sums up to 1, and then we're just left with R over P. All right. And we could attempt something similar for the variance that we did before, but we would have to go into factorial moments, and it may be a bit troublesome. So this first approach is certainly the quicker and the more intuitive approach. The nice thing about it is an easy calculation, but it also develops quite a bit more intuition for what this distribution is doing. Having that intuition is going to help us to be able to answer solve additional problems and answer questions. So next, we're going to go into some examples in which the negative binomial distribution comes up.